Welcome to the Math 1 lesson summary video for the task too big or not too big? That is the question. This lesson is a Solidify Understanding task, which takes the concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to solidify the understanding that inequalities may be used to represent a given constraint. The solution set of an inequality consists of all points that satisfy the constraint, and the boundary line separates the points that satisfy the constraint from those that do not. We're back with Carlos and Clarita and their pet sitting business. And while Carlos is considering the amount of money that he has available to invest in this new business, he realizes that his dad's suggestion of having 12 cats and 12 dogs is too big. And we discussed yesterday that it was too big because while it met the space constraint, it did not meet the cost constraint. We also discussed in the previous lesson that a constraint is a restriction. And so when we looked at the space constraint, it was a restriction regarding the amount of space that they had available. They had 360 square feet of space. And with the startup costs, they have $1,280 to spend, knowing that it will cost $32 for each of the cat pens and $80 for each of the dog runs. So in this lesson, you're first being asked to find at least 5 more combinations of cats and dogs that would be too big, similar to the 12 cats and 12 dogs that we just discussed, based on the startup cost constraint. Plot each of these combinations as points on a coordinate grid using the same color for each of the points. We're not going to use the combinations that we looked at yesterday, the having all cats, the 60 cats and no dogs, or having all dogs, the 15 dogs and no cats, or having an equal amount of both, the 12 and 12. So you're being asked to come up with at least 5 more combinations that would be too big. Plot those on a coordinate grid using the same color for all of them. The second problem says find at least 5 combinations of cats and dogs that would not be too big based on the startup cost constraint. You're going to plot those on the same grid, but you're going to use a different color for each of those combinations. And then for number 3, find at least 5 combinations that would be just right. So 5 combinations that would use exactly $1,280, and plot those on the same coordinate grid. So you're using a third color. So you're going to have 3 different sets of points. And remember, those points are developed by combining the cats and dogs. So if we had 12 cats and 12 dogs, the ordered pair would be 12-12. And that's where you would plot that on your grid. And then finally, number 4 says, what do you notice about all 3 of these different collections of points? So looking back at the table that we created yesterday for the cost constraint, if you recall, we labeled this C to represent the number of cat pens we could purchase, and each one is $32 a piece. This represented the amount of dog pens that we could purchase at $80 a piece, and then this column here represented the total cost for each of these combinations. So this was all cats, all dogs, and 12 of each. And to purchase all cats, we determined yesterday would cost this much, and we know that that's greater than the $1,280 that they have available to spend. So this combination, 60-0, would be considered too big. Likewise, the 12 and 12 would cost $1,344, which is greater than the amount that they have available to spend. And so that would also be considered too big. So for the first combination and this third combination, if we were going to graph those today, we would graph those in one color. And then if we look at the all dog combination, 0 cats and 15 dogs, that would cost $1,200, which is less than the $1,280 that they have available to spend. So that would be not too big. And so if we were going to plot 0-15, we would plot that in a second color. So yesterday we looked at the exchange rate regarding the space constraint. And what we determined when we looked at that visual model was that the area that it takes, or the area that one dog run occupies, was equivalent to the combined area of 4 cat pens. So we want to do the same thing today, but looking at it in terms of the cost constraint. We'll use the same strategy that we did yesterday, which is to take what they have available, which is the $1,280, divide that by the $32 that it costs for each of the cat pens, and that tells us that we would be able, if we only purchased cat pens, we would be able to purchase 40 of them or house 40 cats. Doing the same thing for the dogs, we determined that we would be able to house 16 dogs if we housed no cats. And so when we look at that as a ratio of cats to dogs, it's simplified. It's 2.5 to 1, 2.5 cats for every 1 dog. This doesn't make sense in the context of our story because we couldn't have half of a cat pen. So if we double this so that we're working with integers, we would have 5 to 2, 5 cats for every 2 dogs. And if we look at it in terms of a table so that we can see what's happening, this is starting out with all dogs and no cats. For every 2 dogs that we take away, we're adding 5 cats. And so these would represent the combinations of cats and dogs that would be just right. And this is what it would look like if we were to graph them. So all of the points in red are representing combinations of cats and dogs that are too big, meaning it would cost too much to have 15 cats and 15 cat pens and 15 dog runs. That would cost more than the $1,280 that we have available. And so that's what all of these points represent. Similarly, we have all of the points down here in black, which represent combinations of cats and dogs that would not be too big. So 10 cats and 5 dogs. That would be a combination that would cost less than the $1,280. And then all of these points in green represent points that are just right. So 15 cats and 10 dogs would exactly work. We would use up all of the $1,280 that they have available to spend. We can also see that our x-intercept here at 40 represents all cats, 40 cats and no dogs, and our y-intercept at 16 represents 16 dogs and no cats. It's also important to notice the relationship between the points that are just right. It's a linear relationship. And so we'll talk about that a little bit more in just a moment. Number 5 says, write an equation for the line that passes through the points representing the combinations of cat pens and dog runs that cost exactly $1,280. And what does the slope of this line represent? So looking at the graph that we just created, now your points may look a little bit different than mine. These green points should be, at least the 40 and the 15 should definitely be the same. And remember, we need to use integers. So it really wouldn't make sense to have combinations of cats and dogs that weren't whole numbers. Now, combinations that you found either through using a table or guess and check, whichever strategy made the most sense to you, you may end up with different points up in here or down below. So we're trying to come up with an equation, and remember we can write the equation in either slope-intercept form or in standard form. They're both equivalent. It's whichever makes the most sense to you. So if we look back at that exchange rate, we can use that to help us write the equation in slope-intercept form. We know that to write an equation in slope-intercept form, we need to know what the slope is, and we need to know what our y-intercept is. We can get the slope either from the table or the graph or from our exchange rate. So we know that this is a negative slope, and we also know that we can take any 2 points on this line, and using the slope formula, we can find the change in the y values of any 2 points on this line and divide that by the change in the same 2 points x values. And that would give us our slope. We know that our y-intercept is at 16. We can also use this exchange rate, the 2.5 to 1, to the 2.5 to 1, which is the 5 to 2, cats to dogs. We can use this information to write our equation in slope-intercept form. And the slope represents the fact that for every 2 fewer dog runs we purchase, we can purchase 5 more cat pens. If we look at this in standard form and go back to the table that we looked at from the previous lesson as well as today, we took the amount of cat pens that we wanted to purchase and we multiplied that by the cost of each of those pens. We then added that to the amount of dog runs that we wanted to purchase times the cost of each of those runs, and that gave us our total cost. And so when we look at that in standard form, it looks like this. So they don't want to spend all of the money unless it's going to maximize their profit. Number 6 is saying, it's asking us to shade in all of the points that satisfy the startup cost constraint, which means all of the points that would meet that constraint. And we know that it would not be the red points because we've already determined that that would cost too much money. So they wouldn't qualify. None of those points would qualify. But we do know that the points down here that are in black, all of the points down below are just right points. Those do satisfy our constraint. And so we would want to shade in everything down here in the lower portion of our grid. And we're not shading anything outside of quadrant 1 because it doesn't make sense in the context of the problem. It doesn't make sense that we would have a negative amount of dog runs or a negative amount of cat pens. So we would want to only shade above the x-axis and to the right of the y-axis. And so then we are looking at the points that are actually on the line, and do those in fact meet or satisfy that cost constraint? And we know that the answer to that question is yes. Yes, they do. They would be, those combinations of cats and dogs would cost exactly $1,280. And so number 7 asks us to write the mathematical rule used to represent those points that we shaded as an inequality, or the solution set. So the solution set to an inequality are all of the points that satisfy the given constraint. And so in slope-intercept form, this is what our inequality would look like. And then in standard form, it would look like this. So we are shading all of the points that are less than or equal to that $1,280 cost constraint. Notice that it's or equal to. The or equal to means that we're also including all of the points that are on this line. So because all of this is shaded, that means that any point that lies in this area or along this line that makes sense in the context of the problem would also be part of the solution set. So we don't actually have to have all of the points labeled on our graph. We know that anything that lies within this area would be part of the solution set. And then number 8 asks you to write an inequality to represent the solution set for the space constraint and to shade that solution set for this inequality on a different coordinate grid. And so at this point, you should be able to complete that one on your own. Finally, it asks, what do you think and what recommendations would you give to Carlos and Clarita regarding how many cats and dogs they plan on boarding, and what argument would you use to convince them that your recommendation is reasonable? So remember, when you're coming up with your answer for those last couple questions, you have to take into account both of the constraints, the cost and the space, along with their earning potential, because they want to earn as much money as possible.